let's continue. Yes. The next speaker is Akram Yosri from UGS.
Yes. Okay, so good morning, everybody. I'd like to start with thanking the organizers for making this workshop possible, and also thank them for inviting me to give this talk today. So today I'm going to talk about machine learning assisted quantum control. And before you say, oh no, again, some terrible machine learning and you don't like these things, just wait till the end that maybe you'll change your mind. So I'll start by explaining the different approaches you could apply machine learning in quantum information. And then I'll focus on noise spectroscopy, so I'll start by just reviewing the basics of the theory. Of course, most of you know these things better than me, but just to make sure that we speak the same language. And as a matter of fact, from my experience, it turns out that we do the same things in different disciplines. So I come from, my training was in signal processing, and it took me many months to discover that quantum noise spectroscopy is just spectral estimation, nothing we do.
Yes.
So I'll just make sure that we speak the same language here.
Yeah.
And then I'll talk about some possible applications of machine learning, and most of the results here are preliminary, so some graphs you'll see today, I just got the results yesterday, so it's pretty fresh. Okay, so let's start by a small motivation about why you want to use machine learning. So machine learning turned out to be successful in solving many difficult problems, and this is an example of one of these nice problems. So this is Stanford. They did this helicopter thing. So the helicopter essentially learns how to fly using machine learning. And not just how to fly, but it also learns how to do these aerobatics and these strange movements using machine learning, learning from demonstrations of previous experiences from pilots and so on. And I'm not a pilot, but I assume that these things are even difficult for a human to do. So they have a nice website that has lots of these demonstrations. And the question is really about which is more difficult, controlling a helicopter like this or controlling a qubit. Okay? And you can spend some time thinking about the question. It's an open-ended question, but if you believe that controlling the helicopter is more difficult and we can use machine learning to control the helicopter, then you might be able to use machine learning to control qubits. Okay, so yeah. And the reason it became successful in the recent years is due to two reasons. First, the increased computational power. So now we have GPUs, we have supercomputers, we have all of these things. So the time that we need to do the training has decreased a lot. And the other important thing is the availability of data. So if you are working in image processing, just Google any images you want, you'll download millions of images and you can do your training. Now, important thing to mention at the beginning is that I'm not here to say that we want to replace physicists with neural networks. Okay? This is not what we want to do. In fact, it's the opposite. What we want to do is we want theorists that have these strong mathematical skills to help us, and we want experimentalists to provide us with data. Because I have been working in my PhD for more than 2 years now. Until now, I'm not able to get a single number from a lab. Although I spent 1 month in a quantum photonics lab at RMIT in Melbourne, 1 month going every day from morning till after hours, and at the end, I got a machine learning algorithm without data. So we are lacking data, and we kind of discussed this in the previous days that we need some standardized quantum data sets on which we can do the training and we can test our algorithms. And before we say, okay, machine learning works or doesn't work, we have to do our job. So first, we have to try to use machine learning and then draw any conclusions whether it's feasible or not. But without having data, we cannot really say anything. So it's all about what we are doing now. It's just simulations, and we don't know how these things works in practical situations. Okay, so can say that there are three types of approaches we can use machine learning. The first approach is what I like to call the white box. And this is just a nickname for parameter estimation or regression, whatever name you want to have. So in this case, you have some theory, you have some formula, and there are some unknown parameters, and you want to estimate these parameters from some measured data. So you can think of this as machine learning, and I'm thinking from the perspective of writing software, because we are in the center of quantum software, so we write software, okay? So if we formulate the usual problem of parameter estimation as a machine learning problem, then we can use the available software like TensorFlow and other platforms to solve this problem. And we don't have to worry about implementing steepest descent and all its variants and choosing the learning rates and all of these things. They are already available in packages doing machine learning. So this is the white box when we know a lot about the theory. On the other extreme, we have the black box. So in this case, we know nothing about the theory, and we just put a huge neural network that tries to learn the mapping between the input and the output. And this is very successful in applications like image processing, because there is no mathematical function that can tell me if this image has a cat or a dog. So the black box is very useful in these applications. In the quantum applications, maybe this is not the best approach, because we need to probe some physics from our learned model. And so we might agree that might not be the best way to do machine learning, but still, if we think deeply about it, we can find applications. So one possible application is to use this black box as a simulator. So we know that experiments in the lab take a lot of time. So if we do the experiment just once, collect a huge amount of data, and then learn some model, we can then use this model to predict the outcomes of the experiment without having to do the experiment again. So we can also find some possible applications for this approach. The last approach, which I personally like, is the gray box approach. So in this case, we combine both of these things. So we have a model, we have some theory, and we have a set of equations that we know that it's true. And then we have part of the model that depends on some assumptions. And we want to get rid of these assumptions. So we replace this part of the model with a neural network, with a black box. And so the overall, we can say that the overall model is a gray box. So part is white, part is that we know the formulas, and part is just the neural network. And I'm going to show today some examples of how to use the gray box approach. Okay, so next I will go to explaining a little bit about noisy qubits. Of course, most of you know these things, but yeah, let's just review it quickly. So we have a qubit. Let's start with a qubit without noise. So my example is this qubit, so it rotates around Z, and here we start with a qubit at the plus state, so it keeps rotating on and on. By the way, these animations took me one day to it's nice to see how things look in the blue screen. Okay, so now we have some noise. So this is classical noise, and this comes from interacting with the environment, and under some assumptions we can assume that this is a classical number, it's not an operator. And because now the Hamiltonian is stochastic, beta is some random process, we can describe it using statistics. So one statistic is the autocorrelation, which measures how the samples at different time instants are correlated. If this noise is stationary, which means roughly that the statistics do not depend on time, then the autocorrelation function depends only on the time shift between the samples. And if we Fourier transform this, we get the power spectral density, which is the measure of how much power is available per some frequency. And so if we integrate this thing over a frequency band, we get the power in this frequency band. And the effect of this noise is, as you can see in this animation, is dephasing. So we started with a pure state at the x, and what we end up is just something converging to the completely mixed state, which is dephasing. We lose the off-diagonal elements of the density matrix. And one way to characterize this is using the coherence. So the coherence, by definition, is the expectation of the off-diagonal elements over beta at time t divided by the expectation at time 0. So here we fix the time interval to be from 0 to t capital. And if we assume that the noise is Gaussian, zero mean, and stationary, then we can write it in this form. And we need the assumptions here about that this Gaussian, because this equation comes from the cumulative expansion, and for Gaussian process we have only two cumulants, which are the mean and variance, so we can find the closed form solution. And this is not good, because if we have something like a 1 over f noise, then this overlap integral blows up, and we get a coherence equal to 0, which means that we completely lose the off-diagonal elements. But how we can do this? It's easy. We just do dynamical decoupling, and in this case, we add another term, the Hamiltonian, which is the control Hamiltonian. We apply some ideal pulses. So we have these pi pulses in the along x, and they are phased at time instance t1, t2, t3, and so on. And in this case, when we can write the coherence in terms of this switching function. So the switching function is just something that changes from +1 to -1 whenever we apply a pulse. And the coherence becomes this overlap integral, which we have seen so much during this workshop. And the way of solving the problem is to engineer this filter function such that this overlap integral becomes very small. And this is how we get the usual sequences, CPMG, UTD, and all of these control sequences.
Question.
Yeah.
So sorry, nothing to do with machine learning or anything
Yeah.
like that. But just going back to the previous slide, where so you're saying that if you have 1 on f the alpha for some alpha, that you get instantaneous decoherence.
No, I'm just saying that the rate will be very high, because this number will be this overlap integral will be a large number, and so the coherence will be.
I thought you were saying it blows up.
And the limit, if you take the limit as t goes to infinity, so.
Oh, but that always happens. I mean, even with dynamical decoupling, as t goes
Yeah,
to
yeah, yeah.
infinity, it's going to 0.
Yeah, I understand, but the thing is, without decoupling, it's the rate is the coherence is more. That's why we applied dynamical decoupling to increase the t to.
Okay. I thought you were saying something about some integral going to infinity. No, you weren't saying that.
I just meant
Except
that.
in the long time limit.
Yeah, I just meant that that this integral here. So this is the power spectral density. If it's very small, then this is a large number, right? So this exponential for minus large number, so the coherence is up. This is what I meant.
Yeah. Okay.
Yeah. Okay, so this is about dynamical decoupling, and then in 2011, Alvarez and Suter realized, okay, we can use the same idea to probe the spectrum of the noise, and the way we do it is we apply just these sequences like CPMG, and then we measure the coherence, and then we can estimate the power spectral density of the noise. And the particular details in the paper is that they start by assuming that we can approximate the filter function as take the first harmonic, because it looks like a sink, so we can just approximate it to the first harmonic, and then invert to linear inversion to calculate the parameters, these parameters, and then correct for the truncated harmonics. What we want to do is to start from here and move to the machine learning approach. So the first thing to do is the white box approach, which is essentially the idea of Alvarez and Suter. So in this case, we have a model that has the input, which is the switching function, and the output is the measured coherence. And what the model does is it calculates the Fourier transform of this switching function. And S of omega here is just some unknown parameters, so it's like we're estimating the power spectral density at some discrete frequencies. And so the training set consists of these sequences of like CPMG, for example, and the measured coherence. So the model will predict some coherence, and we have the true value. We can calculate the loss function, and by doing gradient descent, we can change the parameters, which is the power spectral density, and we do these iterations until we have we converge to the minimum of the loss function. And for the experiment, we did this how the loss function. So here we are using mean square error. So this is a plot of the mean square error versus the iteration, and as you can see, it goes down, which means that it's learning something. And the results we have here is, here we have the estimated power spectral density versus the true one. So here in this simulation we had 1 over f noise, and then something like a Gaussian, and then white noise. And as we can see here, that the orange line is the prediction, and there's a perfect match until some point. And here this is not an artifact of machine learning, but it has to do with going back to theory. So here I'm applying CPMG sequences for a fixed time interval until n equals 300. So this is the maximum I apply. So in this case, we cannot probe the spectrum further than some point. And this is known from the theory that if you want to probe the frequency to the spectral density at higher frequencies, we need to apply much faster pulses. And here we can see the prediction of the coherence versus n. So we had, as I mentioned, 300 examples, and we can see there's a perfect match. And this is for testing on UDD. So the training was on CPMG sequences and the testing on UDD, and we expect that this will be very accurate because we are using a white box model. We know the equations, and if we estimate the parameters correctly, then it will work for any kind of sequences. So this is the usual thing. It's just formulated as a machine learning problem, and we are using the usual machine learning software. On the other extreme, we can use the black box approach, and in this case, we don't assume any models. So again, we have the input, which is the switching function. We have the output, is the measured coherence, and put here inside some neural networks. So the LSTM is a deep learning structure that is very suitable for processing sequences. And so when we do the training, in this case, we cannot find the spectral density of the noise as we had from previous, but still we can do predictions. And this might be useful because, remember, in the white box, the formula we used assumes that the noise is Gaussian and stationary. But if this is not the case, if we have more general noise, then maybe the black box approach would be better in this case. Again, we do the training, and this is the example for the results we had in this case. So again, we had 300 sequences, and this is the MSE. Now, it still goes down a little bit weird, has a little bit weird shape, but I didn't have time actually to optimize the parameters and do the usual machine learning. So I had these results 2 days ago, so it's very preliminary, but at least as you can see that the MSE goes down to small values. And the prediction for the coherence, so this is the CPMG, this is where the sequences we use for training, we can see there's a perfect match. For the UTT, it's not a perfect match, but there's much, it's performing almost good for many examples, and yeah.
What did you mean by you did not have to like tweaking the pattern? What do you mean by tweaking?
So usually, when you do machine learning, you have to spend some time to select, you know, the neural network structure, how many nodes, what's the learning rate, things like that. But I'm just saying that.
Randomly or like randomly or just?
It depends a little bit on the experience.
It's an art.
Yeah, exactly. But the thing is that these are just preliminary results. I'm just showing it to convey a message that there is a potential of using these methods. Okay? But as I mentioned, we need to spend some time and efforts. Something to mention about this. So in UTS, for example, we are in the School of Computer Science. We have hundreds of students, and most of them are working in machine learning. 2 out of them are working in machine learning for quantum. So you can say this is the problem, that there are lots of people working in machine learning in the usual context, but there isn't enough people working in this context. And here you need to understand lots of theory. So I spent months just trying to understand what's happening in this open systems and so on. So the message I'm trying to say is, let's try this approach and see what we get.
So your sequences that you're running here, I mean, are you you're not using like an approximation for the filters, right? So you're not assuming that the delta functions are actually taking the full, choosing some frequency resolution and building in there, right?
No, I'm not assuming anything. Just the input is just some switching function, which can be anything, and the output is just measured coherence from doing some simulation.
And are you using multiple repetitions of CPMG and Unity when you do these things?
So the training set, so I'm fixing the time interval, so it's from 0 to t capital, I'm fixing this, and then I apply CPMG for different values of n, so 1 pulse, 2 pulses, 3 pulses, and so on, during the same interval.
Right, so but I'm saying that, yeah, so but you could apply a CPMG, one CPMG, cycle, but for Unity, for example, right, different Unity sequences in different orders, but you're only applying one sequence. So, for example, if it's a Unity 5 sequence, right, you're only applying one repetition of that sequence. You're not applying multiple repetitions within the total time. Because the reason I'm asking this is that the more repetitions you apply, the tighter the filters get. So what you're probably seeing in the UDB case with those extra like little bumps is probably just residuals that you're getting from the other harmonics that are getting that bump, right? So,
Yeah.
whereas if you apply more UDB sequences within this particular amount of time, you probably wouldn't see that as much.
Yeah, I guess so. I have just to emphasize that these are preliminary results, and we need to explore more about what actually is happening in these situations. But the basic idea is, as I mentioned, is just is a simple thing that to apply these CPMG sequences, measure the coherence, and this forms the training set.
What's the difference between the two graphs?
So this one is for CPMG sequence, so this is the training and the testing, and this one is for UDD, so this is testing mode. Okay, so the next approach is the gray box approach, which I love. So this started by collaboration with Gerardo in Griffith. So I went for a visit and we discussed this approach, and this is why I'm emphasizing about the importance of theory. So the way we reach this nice formula involves some lovely mathematical tricks, like having an identity and then splitting it into O squared, and O is some operator, and then the cyclic property of the trace, and magically you get this formula. So if you just get some machine learning person, he will never think about these mathematical tricks at all. So this is the importance of theory. We have to do theory, okay? So this is a double expectation. So this is the quantum expectation, and then we are taking classical expectation over the random process. The first part, which is this expectation OUI dagger OU, which we can call V naught, this has all the information about the noise, okay? And then the second part, which is UC SUC dagger, this is like the control that we apply, and then we have O. Now, if you want to use the gray box approach, it will look like this. So we start with the input is some F is the control we are applying. This is not the switching function in this case. This is the actual F that we apply that gets multiplied by sigma x in the Hamiltonian. And what we have here is the black box part, which its goal is actually to calculate VO. And why you are using here a black box? Because we want to get rid of assumptions, as I mentioned in the beginning. So we can find closed form expressions for this part, for V naught, if again we assume that the noise is Gaussian and stationary. But if we have more general noise, then it becomes difficult to find closed form expressions. So in this case, we can just replace this part, which is V naught, by the black box. And then we have other custom layers. So this is just to take the outputs of the neural network and arrange them in a 2x2 matrix, which is Hermitian, to get V naught. And these layers, this layer is for calculating the control Hamiltonian. You know the usual tricks: move the interaction picture, do the time exponentiate, and so on. So these layers are for calculating these quantities, and we have a measurement layer which calculates this trace. So it takes V naught, UC, and it's parameterized by rho S sample. And so what we get from here is this expectation of the O observable. And so if we want to construct a training set for this structure, what we'll do is we'll choose some form of the pulses, which can be anything, and we apply these pulses to the qubit and measure the expectation and do the training. And because these things are fixed, these are the white boxes, when we do the training, what changes is these parts, the black box, and after we do the training, what we have is this gray box model, which is useful because we can probe points in this model that has some physical significance. So if I look here, this is like, after I do the training, I probe this point in the software. This is an estimate for VO. If I look here, this is the control unit, and so on. So we can actually extract some physically relevant quantities from this model, which is better than the previous case where we had just a neural network. So another useful idea to use this gray box is to do control. So if we want to do control, ideally we want V0 to approach identity, so it's like dynamical decoupling, getting rid of the noise. And we want rho S to be some evolution using G, which is some desired quantum gate. So if you want to use the gray box approach for solving this control problem, if we do this training, then because we can probe these 2 points, what we can do is just pass these 2 points to some optimizer and then find the shape of the control pulses that we should apply such that V0 goes to I and rho S goes to the desired evolution. And we did a similar work in this paper with Alberto Berozzo's group at RMIT Melbourne, and it's available in the archive, which was similar to this idea that we have this photonic circuit and we wanted to find some control pulses to have some desired gates. And if you have time at the end, I can talk a little bit about this. Okay, so again, some preliminary results I just got yesterday afternoon. So what we have here is, again, the MSE, and we can see that by doing the iterations for the gray box, it goes down. Still looking a little bit crazy, but the important thing is that it converges. It seems to converge. If things are going wrong, then what you will see is just the loss function oscillating and never goes down. So this means that it's learning something, okay? And here, this is example again for CPMG and 50D. So the training was using CPMG. And we can see that there's nice match, there are small errors, and for prediction of the UTD also it looks nice. And as I mentioned that we need to investigate some more time to optimize this structure to enhance the performance. And also something to mention that I didn't run the iterations for a long time. So if we run it for more time, these errors will just go on. It will just decrease. This seems very promising, and it's worth exploring this approach.
So is your error like decreasing like 1 over square root n or something like this in general?
So,
Or is it something else?
you mean that?
Like statistically, if you get more iterations or
Well, it depends. I can't say there is particular form. It depends on the structure and the data. So, in some applications, maybe you can have faster convergence. So I cannot really say something general for all data sets and all structures or machine learning structures. And also, this depends on the learning rate. So here I'm just using some learning rate. If we change the learning rate, then this can go either faster or slower. All of these tricks are the usual tricks that people in machine learning do. But again, my emphasis is that without theory, without me visiting Gerardo, I wouldn't be able to think about these things. And so it's really important to collaborate in these kind of projects, and I think this is why you have the Muri and the Osmuri projects. Okay, so now I'm going to show another application. It's not about noise spectroscopy, it's about usual control in a closed system. So in this case, we have a spin qubit, and here we are applying, so it's closed evolution, closed system evolution, and you are applying some pulses in X and Y. And you can think of this like in a superconductor factor qubit, for example, and these are like the I and Q channels. And in this problem, we want to characterize the distortions that happen to the pulses. So physically in the lab, we have this function generator. It generates some pulses, and then it goes through the cables inside the fridge, and by the time it reaches the chip, it gets distorted. And if you want to characterize this, and we couldn't probe what's happening inside the fridge, then again we can use the gray box approach. So in this case, f of t just denotes, so it's like it will be two-dimensional, it denotes the I and Q channels. And we have a black box to model the distortions that happen to the pulses. And then the rest of the white boxes is to calculate the Hamiltonian, do the evolution, and do the measurement. And so to construct the training set in this case, we'll just apply some random pulses. In this example I did, these were some Gaussian pulses, so this is the I and Q. So this is what we think we're applying. And there's some unknown transfer function that results in distorting these pulses, so this is what the qubit senses. And we want to find, we want to have this, to characterize this model. So apply these pulses and measure the expectation of, like, measuring the expectation of spin up or the probability. We can do whatever measurement we want. And we do the training. And again, we can see here that for this example, we have these Gaussian pulses. The loss function, the MSE, goes down, which means that the structure is learning. And this is an example for the testing set. So here we had 50 examples of just random Gaussian pulses that were not in the training set. And this is the probability of measuring the qubit to find it in spin up. And we can see there is also a perfect match between what we have here in from the simulation and what we have from the prediction of the machine learning model. So this is very useful because now if we have this model and want to do some control, we can add here some additional black box which takes some desired target expectation as an input and generates the correct pulses that we should apply to get this this desired outcome. And also the preliminary results shows that this extra, adding this extra layer works, and we can actually do control using this approach. Okay, so for the last application, this is the one I mentioned, which was about doing this photonic circuit. So we have this photonic circuit, and the experimental setting is that we have this optical chip, and what we can measure is the optical power at the output, and we cannot measure any voltages inside this chip. And what was happening is that when we apply the control pulses to control the behavior of the chip, it gets distorted, and we cannot characterize this because there's no way to measure these voltages. So again, we constructed the gray box approach, and so we do the training, and we have a model for the chip, and then we add the extra layer for control. And in this example, we had this sequence, so we wanted to implement a sequence of quantum gates using this this chip, and this is how it looks like for this is an example for the gates we have. So we have this sequence like permutation between waveguide 1 and 3, and then we have other merge, and then we have permutation between 1 and 2, and so on. And this is the kind of control pulses that we get from here. And the nice thing about these control pulses are that you can see here that they have these distortions which actually fixes the distortions already introduced by the chip. So it's like undoing the distortions, and at the same time it's doing quantum control because it's getting the gates. So these levels are what's resulting in implementing the different gates we have. So this also was a nice application. We're still waiting for the experimental group to provide us with the data. So again, everything is simulation. But it's very promising, and the papers on the archive, if someone wants to have a look how to use this gray box approach. Okay, so to summarize, we discussed today three approaches to do machine learning. The first approach is the white box approach, which is if you know the theory, then we can formulate the usual problem of parameter estimation or regression as a machine learning problem and use the standard software. The other extreme is the black box, where you assume nothing, you just put a huge neural network and let it learn everything. And then there's the gray box, in which you know part of the theory, and then you want to get rid of some assumptions. So you replace the part of the model with a neural network to get rid of these assumptions. I showed some preliminary results on noise spectroscopy and control, and it seems promising, and we need to investigate more time and efforts to explore this direction. And as I mentioned, we need theorists, very important, not to get rid of them. So we need these theorists to help us formulating the problems and see what are the assumptions and what are the strong assumptions, what are the weak assumptions, and so on. And we really need the experimentalists to help us and generate data sets, because most of the work is about simulating qubits, and we don't know how these things work in real life. So we are dying for that. Okay, so the take-home message is everyone should get a gray box. So if you're doing theory, do a gray box. If you're doing experiment, get a gray box. If you're doing both, also have a gray box. Everybody gets a gray box. Okay? Thank you.
Great job, thanks. Any questions?
So, the results you showed on building essentially a simulator towards the end there, were you showing, keep going? Right there. So in this case, your error model is, is very simple. Obviously, you're trying to sort of, do some initial testing to see if this method actually works.
Yeah.
I mean, any thoughts on sort of, if you were trying to do this beyond a single qubit system, right? That would be kind of where you would really sort of potentially see the utility here. If you could model something that would be like a multi-qubit system without actually having to do the full dynamics. So any thoughts on sort of, the sort of complexity bounds in that? I mean, right? Because at some point I shouldn't be able to, exactly approximate a multi-qubit system with, I should have some complexity argument that tell me that I can't do that any more efficiently here, at least exactly, right? But approximately I may be able to do something like that. Is there any, is there any reason to believe that you can do sort of multi-qubit systems, or anything from machine learning that discusses sort of the complexity of systems that you can approximate?
So for the project I was working on, the photonic circuit, it wasn't a qubit. It was a three-dimensional system. So in principle, we can extend this to multi-qubit. The thing is, you can think of like yesterday's Nora's talk about quantum encoders. So quantum autoencoders. So maybe we can find some efficient representation of the dynamics. If we replace some parts by these black boxes, then maybe we can find some way to compress the information in the dynamics. If you are willing to find some approximate results, not exact results. So I think it's worth exploring this. Yeah.
Any more questions?
Did you have any more conventional benchmarks to compare against? So it's clearly great, but did you try and compare it to a simpler model, like sort of just a linear system that has got easier ways to recognize?
In the project I mentioned about the photonic circuit, the data fitting they had with the linear models, the fidelity was about 80%. So it was not fitting with the usual linear models that they used actually to design the chip. Using the machine learning, we could get more accurate results. And for the control applications, using simulations, we got fidelities like up to more than 99%.
So the other aspect of that problem is that we've got certain cases where you have like only 2 channels of control and you have a larger orbit space, like 3 or 4 qubits, where you've got controllability, but it's much more complicated how to exploit the dynamics of the system to achieve the goal.
For this type of Hamiltonian, I only considered 1 qubit. We didn't consider higher dimensional spaces, but again, yeah, it's worth exploring and see how things work. Yeah, there are actually lots of ideas, and all the time working with Chris, we have every now and then we get some idea. Okay, we need to try this, we need to do this, and the problem is that every week we start a new project, and then nothing is finishing. And I'm only one person.
Sorry, my bad.
Yeah, so I think we need some more
I didn't think
people.
he was actually going to do everything I suggested.
Great.